Right, I guess let's get started. Good evening, everyone. Thanks for joining NSCS Colloquium. Today we have pleasure of having Ilya Sergey as our speaker. As you know, CS Colloquium intends to celebrate recent promotions and awards. And in this context, Ilya received his tenure last year. So we are very excited to have him as a speaker and also use this as a proxy to celebrate his tenure. He's an associate professor at the School of Computing at NUS, where he leads a verified system engineering lab. He also holds a joint appointment at Yale NUS College and is a lead language designer at Zilliqa, which is a fintech startup. Before that, he held a postdoctoral research position at India and a faculty position at University College London. And long before that, he was a software developer at JetBrains. He is recipient of a lot of awards, just to name few: Distinguished Paper Awards at Popl and PLDI, the 2021 Yale NUS Distinguished Researcher Award, and award from Google Faculty Research. We are very excited to have Ilya as our speaker, and the floor is yours.
Thank you so much, Deep. And first and foremost, thanks for organizing this colloquium seminars. I think they've been quite instrumental for disseminating the information in the department on who does what. That's always very welcome, and that's one of the highlights of being at SOC. All right, very happy to be here and very happy to see so many of you joining today. And I am very excited to share a story of a journey that I've been following as a pretty big part of my research for the past 3 or 4 years. And this is something that kind of brought together a lot of different topics that I've been working on throughout my research career, focused around programming language technology and combining things such as type systems, semantics, program analysis, and in general programming language design. So today the topic is going to be quite timely. I'm going to talk about programming and programming languages for blockchain, and the story is going to revolve around one particular programming language that I've been a part of and I co-designed with multiple colleagues and collaborators. So the title of my talk is Growing a Smart Contract Language from Safety Net to Springboard. So, and without further ado, let me just start with the story. So in the beginning, there was the exciting technology called blockchain and the distributed decentralized consensus by means of blockchains. And in case if you know nothing about that, which is highly doubtful, but nevertheless, let me give you a very short intro to the technology. So imagine that we have a number of transactions, which can be absolutely anything, just some orders, some objects which come unordered, and we have a goal to put them in order in a decentralized way. So multiple parties need to agree on whether they go in one order or another. And this is a classical problem people study and implement in distributed systems, which is called distributed consensus. And the consensus should be reached on what exactly the order of the transactions should be. So, there are multiple ways to reach the consensus in a distributed setting, having different guarantees when it comes to fault tolerance and what kind of faults they might tolerate, and also how decentralized they are. And one particularly prominent proposal was known as Nakamoto consensus since 2008. That's what people mostly know as blockchain consensus nowadays. And the idea is very simple. So how can we make sure that the transactions come in the same order by sort of bidding on the different proposal and accepting one of them uniformly. And there is a certain amount of cryptography involved into how to make this agreement uniform and make other proposals non-competitive, but I won't go that much into detail. So the bottom line, the distributed consensus is about ordering a sequence of transactions. Okay, so transactions can be anything. And the idea of the blockchain is that we don't really want to agree on the particular order of the transactions, taking them individually. Rather, we want to order them into blocks, and transactions going to be ordered within the blocks, but blocks are what's going to be proposed for the distributed agreement, and we are going to agree on the order of blocks which will form the chain, hence is the name of the technology. So let's zoom in on what exactly these transactions might be, so we are interested in ordering. So typically they are just some commands on how to alter otherwise replicated state. So each participant of the consensus has certain nodes, so we can think of transactions as commands how this state needs to be changed. And the simplest variant, which also came with the primary application of the technology, is implementing a distributed ledger that keeps track of some digital currency in the amounts associated with different accounts. And those transactions will be simply transferring funds from account A to account B, and the consensus would be required to know that there is no double spending. So like if A has spent certain money, everyone has a consistent view on how much money A has left on their account. So more interesting, and this is something that has been realized very quickly, is that we can add arbitrary logic to these transactions. And furthermore, we can use the transaction protocol to piggyback the deployment of the distributed applications on top of the blockchains. And those distributed applications, which run by means of submitting transactions, is what we currently know as smart contracts. So smart contracts have been a very versatile technology, and their applications and the interest in this research community from different perspectives has been skyrocketing since 2015, since Ethereum, as a main competitor of Bitcoin, has introduced them into the circulation. So the idea of smart contracts is that now we have this not just replicated state, but we have replicated state split between multiple replicated objects. And if we want to mutate those objects, we can do so by means of transactions that are accepted or rejected by taking the distributed consensus. So state, again, typically includes some amount of funds or virtual currency, and there is one or more entry points. So the transactions can say execute this function of the contract that will do certain things, or the other function, and this is how they typically are being used. So the contract, they are reactive, so they cannot do something on their own. They just expect for the user to initiate the transactions, and there might be some chain transactions of contracts invoking other contracts. So the list of usages keeps growing, and every year we see more surprising applications. So initially it started from something more like decentralized auctions and crowdfunding campaigns. Nowadays the non-fungible tokens is a big applications, but also there is a lot of usage in voting and arbitration and games and distribution of rewards. And I hear people now use smart contracts to do some accounting paired with Facebook metaverse, so which is rather crazy. So, and there is also quite a few platforms that adopted different takes and different technology for smart contracts. So Ethereum was pioneering one. Then there were like Tezos, Libra, Cardano. Some of them no longer active, some of them have appeared. So this is obviously not a complete list. So in case if you have never seen a smart contract that is deployed in Ethereum, this is what it usually looks like. I don't suggest you go and try to understand the code, but from the looks of it, you can see this is actually very similar to your standard object-oriented program you write. So this is a contract that does accounting, so it has an owner that has some rights to do particular operations with it, and also has the field code mapping that tracks how much funds different accounts associated with different addresses have. And it also has a method that allows to invest, i.e. introduce some amount of money into this contract. So all in all, it looks like very standard Java objects with constructor, mutable fields, and entry points. However, in disguise, it's actually a reactive object. So it also accepts what's called messages, which is how the methods are invoked. It implicitly accepts certain funds, and it even can be called indirectly from another contract that got invoked by a transaction. So in fact, the model is actually more interesting than what you can think just by the looks of it and using your object-oriented intuition. So in fact, it's so interesting that it's very easy to sneak in some behavior that might come unnoticed, that how I just introduced this function with a very telling name, steal money, that just takes all the investment that has been stored in this contract and in state and transfer it to the account of the owner. And this kind of raises the questions, why do we even trust smart contracts? So how can we make sure that they don't do or cannot do what we don't expect them to do? Because after all, it's a contract. So that's an agreement between the multiple parties. And this is a crux of the problem. So these are the programs, but they're very critical problems. So it's better if we manage to reason about them rigorously. So as they have been introduced, the smart contracts came with a certain predetermined aspects that have been taken for granted by the community. So smart contracts, what I've shown you is a high-level language representation, but the way they are deployed as pieces of data on the blockchain is in a relatively low-level language, which is pretty difficult to read, but it makes a uniform compilation target. So they also, the language in which they're defined is tune complete, which means that you can write literally anything. and this is ostensibly a good thing. And finally, the contracts are the only things that determine their own correctness. So in order to understand what the contract really abides you to, you really need to understand the code, which is kind of difficult if you remember that the contracts are typically replicated in some sort of low-level assembly-like language. So there are nothing like a written low contracts that we can think. So with that comes the corresponding shortcomings. So the contracts are difficult to audit and difficult to verify formally. They have complex semantics and prone to exploits, and every month we have dozens of papers on more exploits in smart contracts. And finally, the fact that the only way to assess the correctness is to read the code is pretty unsatisfying, because that requires a lot of expertise, and sometimes it's not even tractable. So as an example of why contracts can be made very easily incorrect, here is a case which made it to all the news, and that's what essentially made the research on smart contracts so popular from the formal methods perspective. So here's a contract that implements the accounting, and it allows to withdraw the balance, but somehow the withdrawal of the balance, according to the semantics of the language, coincides with calling another contract. So what this contract can do is just to try to withdraw again and again and again. So you can think of this reentrance loop, and only after that, after the contract is depleted, the other adversarial contract can stop withdrawing. So this was known as the DAO attack, by the name of the DAO, a very famous contract. And this provoked a lot of interest in how should we really write smart contracts, what are the good practices and what are the ways to structure them. So clearly that looks like a problem for programming language design, and this is why it was of my big interest, but not just mine. So there was a whole community after that. So the question everyone was asking was the right thinking model about smart contracts. And this is where my journey to that began. So it began from an analogy. I love analogies. So they are very useful in programming languages in explaining things, but also in introducing things. So back then in 2017, I teamed up with, back then I was not at SOC, I was at UCL, but I teamed up with another researcher at SOC, Aquinas Cooper, and we wrote this very high-level paper for a workshop called A Concurrent Perspective on Smart Contracts. And the idea was very simple. So there is a lot of body of knowledge about how to write concurrent software in the community. So can we apply all this knowledge to write smart contracts in a similar way? And the analogy was that the smart contracts on the blockchain are exactly like threads so accounts using smart contracts are exactly like threads using concurrent objects and shared memory. So smart contracts in some way are concurrent objects, so the same principles for bug detection, but also for structuring them should apply. And this was an analogy that we managed to exploit like almost immediately. For example, this idea of re-entering the contract before it has completed its main operation and depleting its state, this is something that you can think of in terms of concurrent interaction between multiple threads on a single object. The idea here that when you implement a concurrent operation, you typically might switch between multiple threads that use the same concurrent object at the same time. So in the case of the DAO smart contract, the withdrawal was allowed to switch the context, so to say, and let the other contract take the execution lead and then call the original contract. And this is actually very similar to a situation that we have in the concurrent setting when we have a concurrent object like a stack or queue that is being used by multiple threads simultaneously. So the way to design this object so nothing bad would happen is to make sure that every time an atomic section is left by a thread, it restores certain consistency invariance of the concurrent object. So this is the main principle of designing robust concurrent software. So whenever we switch the context, we make sure that the object invariants are preserved. I'm not going to go deep into detail what exactly should be the invariant in the case of DAO. Let me just tell you that this invariant did not hold upon the re-entrance of the contract, and this is exactly what was exploited. So should the authors of the contract kept this concurrent intuition in mind, obviously that would not happen. So the analogy turned out to be quite rich. So if we extend it further, we can also see other interesting applications of smart contracts. Like, for example, smart contracts are not active, they're reactive. So if we want to make the smart contract interact with the real world, like get some data from the weather forecast or anything, typically what's happening is that we can make the smart contract to emit a request to another contract that will notify the client that is outside of the blockchain. And this is typically as much as we can do in the scope of one transaction, because we cannot wait for the client outside of the blockchain to get back to us immediately. So this transaction is usually followed by another transaction where the client outside of the blockchain calls the contract back using the callback, very similar to what we do in React.js, and in concurrent applications with the required data. So altogether, this filing the request and getting the data in the callback forms a single logical transaction that's like calling and returning. However, the problem is that these two parts of the same logical transactions can very much be in different blocks. So they are the parts of the different physical transactions. And obviously more transactions might pile up after the transaction one has taken place. So this is not great because the state we left the blockchain at the end of transaction one might have been quite different from the way we encountered at the beginning of the transaction two. And this is exactly, so having this intuition, we looked for these patterns and we found exactly that in a bunch of online games where there was some random number requested from outside Oracle. So using this Oracleized query at the beginning. And then there was an expectation for the response to this query in the callback method. The problem is that the IDs of the sending and receiving the request were handled improperly. And as a result, this function was prone to rewarding a different player, a wrong player, with an amount of money. And that was exactly because this transaction, logical transaction, has been split into two components and the proper atomicity of the logical transaction has not been enforced. And obviously the language did not allow that to be enforced in any way. So in other words, the non-determinism that we typically see in concurrent application is very similar to what we see in smart contracts, which you can phrase in terms of the data races. So this analogy was useful, but what can we do with that? Well, first of all, we can start writing papers about exploits. And this is something that I was very happy to do. So we teamed up with Aquinas and Pratik, who is also an associate professor at SOC, and Ivica and Ashish, who are also in Pratik's team. And we wrote a bunch of papers on using this concurrency analogy. And then there are other researchers who use this analogy to write papers about exploits. So that was fun. But that doesn't really solve the problem that we still have like lots of ways to write broken applications. So can we really fix it? Or rather, can we avoid those patterns with better programming language design? So and the goal of programming language design, to be precise when applied to smart contracts, is to enable rigorous reasoning about high-level behavior of smart contracts. Any questions about the presentation so far? I really cannot see anything except for my slides. So if someone has a question, please just unmute yourself and shout. And feel free to do it anytime during the presentation. All right. Nothing. Oh, right. Let me actually slightly change the view so I could at least see who's around. Okay, good. All right, moving on. Okay, so we want to enable rigorous reasoning about what our smart contracts do. Okay, let us proceed with this to chapter 2 of my. Yeah, okay. Who has a question? Yes.
So this is Umang here.
Yeah, please go ahead.
So you said that you want to design a programming language and enable rigorous reasoning.
Yep.
One could ask, why not maybe use an existing language?
Well, okay. So that's a good question. Why not harness the existing language for rigorous reasoning? This is obviously something that one can do. The problem is that back then in 2017, the field was still new, and I believe it still is. And everyone was hopeful, including myself, that we won't get into the state with which we are with JavaScript nowadays. So having observed a number of bad scenarios, we will be able to prevent that with alternative programming language design, while the field is not yet so largely developed. And that was the reason. And also that will hopefully save us lots of trouble in writing extremely elaborate and potentially unsound tools that deal with all the complexity of existing technology, which back then was just Ethereum and Solidity. So whether this was the right choice, the time will show, but it certainly proved to be a good decision, at least in the case of one ecosystem, to invest into doing a new programming language rather than trying to do something about the existing ones.
That answers my question, but just looking forward, is it the case that the language that you're going to talk about will have, let's say, restricted behavior, and that'll sort of eliminate?
Yes, it will have restricted behavior, and it will have stronger static guarantees.
Okay, makes sense. Thanks.
Thank you, Monk. All right, let me move on, and feel free to interrupt. Okay, so on to the second chapter, which is about the prototype. Okay, so whenever a programming language person tries to design a programming language, they usually start from trying to encode its semantics. And the best tool for encoding semantics, in case if you didn't know, is called the Code Proof Assistant, a vastly, an extremely famous framework that allows for rigorous formalization of mathematical facts, but also of for writing programs and proving facts about them. So bottom line, Code Proof Assistant is a state-of-the-art verification framework. It's based on dependently typed functional programming. It's interactive, so like that's the price to pay for its expressivity. It's not the push the button verification, which you can have in multiple restricted domains. So here you are really in for the full power of higher order logic to encode the formal theory that you're interested in. It has very small trusted code base. Why is it important? Well, that means that we actually have very low amount of code to rely on when the proof assistant tells us that certain things are true or not. So, and that code is what is trusted, but the smaller the amount of this code is, the better it is. And COC in the past 15 years has been immensely successful to implement large systems such as compilers, operating systems, and even distributed protocols, including toy versions of blockchains. So if you're interested more about in that, I can talk more, but that's not the part of this talk. All right, if you have never seen what the COC interactive mode looks like, this is more or less what it looks like. You run it in your Emacs, you run the program, and then you start interactively executing it. And whenever COC encounters a certain fact that marked as Ethereum, it asks you for a proof. And then you type the proof next to your program and next to your definition. And overall, the program looks like something you would write in a functional language, such as Haskell and OCaml, but the proof looks something like you would write in a very kind of programming style looking mathematical notation. Okay, so the nice thing that you can encode semantics of something like smart contracts relatively easily, saying that the contract is just a protocol and it behaves according to sends of like a bunch of messages, and these messages form the schedule, and according to each message in the schedule, the smart contract makes a step. So altogether that forms a semantics of the language, which is not immediately usable as a programming language, but it's already something that we can reason about and we can encode facts about. So that gives us a model. And as a model for smart contracts, since they already sort of trying to be this thing, so we decided to choose just simple state transition systems such as actors in actor-based frameworks. The interaction between contracts is done using sending and receiving the messages. Messages trigger the transitions, but otherwise the transitions are atomic. So there is no way one contract calling another besides sending a message. So the interesting thing that most of the computations that the contract do, they are internal to them and their state. They really don't require that much interaction. And furthermore, they don't even require that much of state modification. They can be just done using pure expression. And the humanity is really, really good to reason about expressions. It's less good than reason about effectful programs. So, and the contract state includes just a bunch of immutable parameters, mutable fields, and something to keep a track of the balance. So when you think of the contract interaction now, there is actually very clean separation about what the contracts do internally and how they communicate that to other contracts. So typically a transaction will start by a certain account registering the message to the contract C, and when the blockchain consensus execute that, this contract C might generate more messages that will land in other accounts or in other contracts that also might impose the circular behavior, but they will not be reentrant. The reason is that the message M6, even though it comes back to the contract C, it will be processed after the contract C has done its current logic. So there will be no breach of the invariant, and this is something the language guarantees by construction. Okay, the nicer thing that if we zoom on these contracts in isolation and how they proceed from one of their state, that's typically called configuration, to another as a result of the receiving messages, then we can really abstract over the behavior of one contract and how it's related to the behavior of the another contract. So even if these two contracts are malicious and they are like specifically trying to do something bad to our contract C, the only way they can do it is by sending particular messages to the contract C. So now we can effectively prove the facts about the contract in isolation, saying that whatever messages it receives, in whatever order, it will always end in safe states and will always make progress. So for that, we can start defining logical connectives that combine multiple predicates. So this one looks somewhat little bit intentionally gibberish. It says that we can assert that if the contract P initially is in certain state satisfying property P, then from some point, then it will always be in the state satisfying Q from there on, as long as a certain condition on the received messages holds. Okay, so like starting from P, ending up with Q, and R holds on the intermediate messages. So if you think why this might be even useful, so why do we need this definition? Turns out that surprisingly many properties that people care in the financial technology world, they fall into this model. So like, for example, token price only goes up, or no payments are accepted after the quorum is reached, or no change can be made after locking. So this is like fairly standard way to formulate safety properties. Consensus results are irrevocable. And if we have a language that by definition allows us to have all computations fit in this model, so we can state this property, which is something that is very difficult to do on Ethereum, where there's a lot of interfering in the interaction, then we are good. Then we can start proving theorems about the behavior of their contracts, and we can start proving them using the power of tools such as Coq. So we can encode this definition as a just definition in Coq. So this is just to show you what it would look like. It's maybe a little bit scary, but it's not that far from the mathematical notation. And then we can take something like a fairly common contract for crowdsourcing, think what should be its parameters, what should be its state, and what should be the ways to interact with it. So for example, one can donate, one can get funds if they are an owner and the campaign has finished, or some can reclaim their donation to this crowdfunding contact if the deadline has passed, but the goals haven't been met. So this is a fairly standard way to do the crowdfunding, something that you might have seen on systems like Kickstarter, but obviously that can be done using smart contracts. So now we can specify the properties of crowdfunding in plain English. For example, the contract will always have enough balance to refund everyone. It will not alter the contribution records. Its contribution will be refunded. And then using this logical connective, we can effectively embed that into the same system in which our programming language is defined. So saying like, for example, some contract donated the amount, it didn't try to claim, then it means that its record will be preserved at the end. And again, written in the programming language of Coq, this is something that is very similar to mathematical notation. So this is great. So now we have a language with clean semantics that allows us to prove the property. So what else can we do with this language? Can we make it realistic? Well, this is where I was kind of ready to just write a paper about that, saying, like, look, this is a good model. Maybe people should adopt it. I'm not sure what to do about large-scale adoption, and this is where things brought me to NUS, and I think this was a big stroke of luck. So about that time, 2016, so Seth, Pratik, and their affiliates published a very influential paper called Secure Sharding Protocol for Open Blockchains. So that was published at CCS 16. And shortly thereafter, some subset of the authors founded a company called Zilliqa, which started in Singapore, and they went public in August 2017. So the proposal was about a distributed protocol and how to implement it, but that protocol at that time did not quite have a smart contract layer. So that was a very unique opportunity to do something from the clean slate in the real work environment. So I was visiting this beautiful place back then, and I got to talk to Pratik, and he suggested that we should team up and try to deploy this language on the real blockchain. And from there, I took off my theoretician hat, I reasoned about semantics and whatnot, and I started to think what would be the minimal language in which A, people can write smart contracts that are practical, and B, we can still have these properties. So there was kind of a wish list that we all agreed on. So this smart contract language should avoid basic problems such as re-entering. So it should be also kind of minimalistic, so we could maintain it with a small team of engineers, and we could formalize it and build tools for analysis and verification with low effort on it. So this is obviously a very famous trade-off, because the smaller your language is, the harder it is to program it, but the easier it is to build compilers for it and to analyze it. So like the big point was how to make this language minimal and small, but still expressive, so we can implement common patterns of programming smart contracts. We can make it verification friendly, and hopefully performance wise, it shouldn't stay on the way of this performance sharded consensus protocol. So overall, we were like targeting to solve these challenges. And again, the way to target is to look at the past 60 years of research in programming languages and see how expressiveness and minimalism can be combined. So to that extent, we decided to revise our understanding of smart contracts and try to distill what's the essence of smart contracts as programming model. And turns out it boils down to really like 4 components. I mean, you can add more, but this is our view. So the contracts, they perform certain computations. They alter their own and each other's state. They have certain effects such as accepting or rejecting funds, or also logging events in the distributed ledger. And finally, they communicate with each other. And turns out that these 4 aspects is something that existing language already could do, such as solidity, but the way they do it is kind of extremely convoluted. So in fact, state manipulation can be part of the computation and also might involve certain communication. And this is what makes this clean model that allows to state safety properties so difficult to achieve in Ethereum context. So either you need to write them in a particular way, or you need to do like very, very heavy processing of them, which I don't think the community has figured out how to do yet. Okay, so what if we try to disentangle those and structure our programs as this? So like first we have the computations which are kind of specified and verified, and on top of that we have state manipulation, and finally at the top level we have communication between the contracts. And we have clear abstraction levels in terms of types and specifications between these aspects of our program. So this is where the abstraction boundary goes, and we try to design the language around this concept. So the language got the name Scilla. So in case you're curious, so Scilla is this beautiful town in Italy. Apparently it's also this endemic plant in Northern America. Actually, I didn't know either of those. So the name was picked because it was supposed to be a smart contract intermediate level language, and Scilla with Y was already taken by a database. So yeah, so together with Aquinas and Amrit, who is now a president of Zilliqa, back then he was a research associate in the security group, we wrote this proposal. So, and we adopted the following principles from programming language design. So for computations, we took this small calculus called systemf, which is the basis of most of functional programming languages nowadays. We make the contracts non-Turing complete, allowing only for primitive recursion and iteration. All effects are explicit and expressed as state transformer semantics. And finally, what we have already seen, the communication has been done explicit by means of phrasing the contracts as actors. So just a very quick glimpse of on the syntax of the language. It's very small. So these are literally all the types you can have in the language. You can see some interesting nuggets at the bottom, where we have essentially what corresponds to generic. So we have universal types, parametric types. This is the whole functional component. Again, those of you who are familiar with Okama or Haskell can recognize some components. So this is kind of a very verbose small subset of OCaml. And finally, we don't have loops. We actually turned out that we don't need them if we have higher order functions. For example, loops, they are used to iterate. And something that as simple as iteration can be expressed as this combinator that takes a natural number, says what to do for 0, what to do at each iteration, and what is the number that needs to be taken, and that gives you the result. So this is something that you can very effectively compile a loop to. So that's why we really didn't need to have loops in the minimal language. We can have loops, and we do have loops as a syntactic sugar. So you can write your Fibonacci function in this way. So when you start from the pair and you accumulate that, and eventually, and you accumulate it with this iteration, and eventually you get the result being the nth and n-1 Fibonacci number. So that might look a little bit baroque, but again, remember, this is a small language. You can write pretty much all you want in it. And also we have a compiler that, we have a compiler that allows to reduce the amount of this clutter. All right, so we can also iterate over other data types, such as lists. So for example, take the empty list, take the operation what to do at each step of the list, and take the list itself and return the result. So all these operations default into generic class of faults. They're extremely well studied, and they're very easy to incorporate into the statements of safety results and the theorems. Okay, so I'm just skipping through some details. So basically, you can implement lots of stuff with it. Finally, we have the imperative fragment of the language, which is very small. So it's just assignments, reads, pattern matching, which is a stronger form of conditionals, and interactions to read from the blockchain state and accept funds and send the messages. So altogether, like this is what a standard contract in Scilla looks like. This is a single transition of the crowdfunding. It has some amount of boilerplate, but again, this can be reduced with high-level syntax. It's not really our concern. The point is that the whole definition of the language fits into 3 slides. Yeah, so these are some readings and some writings and some acceptance of the funds. And what's most important, formation and sending of the messages. So those of you who have experience with languages like Scala or Erlang can recognize that this is actually very similar structure. Okay, so just to conclude this part, now we have this language. What are we going to do with the contracts? So the idea was actually slightly controversial by that time, but this is nowadays mostly accepted in all the similar proposals that follow ours, that we are not going to deploy some sort of low-level language like assembly or EVM. So we are going to deploy these contracts themselves. So that's going to make it easy for the contracts to be verified and audited. And furthermore, if all the contracts are deployed in this form and we can syntactically distinguish between computations and expressions, we can allow for a lot of code reuse. So now we can think of the blockchain as a big repository of functional code that can be reused between the contracts. And this is exactly what one can do. I see one question in the chat. Let me pull it and see what's about. Why is pattern matching effectful? So, okay, Kieran is asking why pattern matching is effective. So, pattern matching is not effective in the sense that the match is pure, but we need to have some sort of branching constructs in the effective statements. So we could do it with if, or we could just do it with pattern matching, the way OCaml does it. So that was the reason for the choice. I hope it clarifies it.
Yeah, I have one more question.
Yeah.
So why are you staying away from compilation and sticking to an interpreted mode?
Okay, so the reason why we're staying away from compilation. So this is actually a really good point. So, and this is something that the community doesn't have a clear consensus on. What should we deploy as a contract? Should it be some sort of structure like source, like kind of high level-ish, intermediate level-ish language with good control flow structure, or should be the assembly? And the pros for doing the assembly is that, well, it's a compilation target. So you can have multiple, like probably have larger freedom in your high-level languages. Like, for example, multiple high-level languages for EVM exist. With the downside that you will have to deploy the code that is effectively impossible to audit, and it's very easy to miss exploits in it. So if you want to have what we have, like more high-level language on the blockchain, well, then you certainly reduce the space of what kind of higher level languages you can build on it, but you are allowed to deploy the code that is ready for audit and comprehension. You can still have a compiler, but that is actually going to be kind of tricky, and I can tell more about that in the end of the talk. So we are building the compiler, but this is a compiler that runs on each individual client. So the point is here, like smart contracts can be stored locally in any way you like, in any way you like to process them, and as long as you produce the results that are compliant with anyone else's expectations. So it's kind of a little bit tricky to produce a good compiler for smart contracts in a way that it preserves the intrinsic costs, such as gas. And this is something that other systems with similar proposals are going to face or are facing soon. So like basically it's very easy to define the clean model in the intermediate language, but if you want to build a compiler that is fully semantics preserving, it's kind of complicated. So yeah, I don't know what's the right answer here. I think it's good to have the code, the replicated the code that we know the semantics of, and that was a conscious design decision. I don't know if it answers your question or not.
No, it does. It does. Thank you.
Okay, good. All right. So yeah. So the nice thing about having minimalistic language, let me go to the full screen again. The nice thing about having minimalistic language is that the implementation of the core component that is very small. So the core interpreter, which is written in a particular programming style called monadic style, is just about 200 lines of code of OCaml, which is the best language for doing compilers. I will try to make this point clear in the next semester if someone has taken this class. So whenever we needed to change something in the interaction with the blockchain, because that was essentially concern of the state, that is something that did not require the change in the core logic of the interpreter because of this style of programming, monadic style. And this is also how we managed to fix lots of performance bottlenecks, like introducing continuation passing style without altering the semantics. Okay, so that, yes.
More like a comment. So who are the end users for writing the contracts in your language?
Okay, so who are the end users? Well, surprisingly, just the regular people who want their domain-specific logic, like a blockchain storage for an online game to be deployed on the corresponding blockchain of choice, in this case, Zilliqa.
So is it fair to expect that such people would be conversant with the functional style of programming?
In effect, that's surprisingly what started to happen. So since the community was so vibrant and way less conservative than, let's say, the community of front-end programmers who essentially like only love JavaScript and versions thereof, they were very willing to study. So there were quite a number of workshops organized not by us. I will have a slide about that, which taught people how to program in a functional language with the recursors and iterators, and people got surprisingly good writing the code on it even before we rolled out some sort of high-level language that makes it slightly less painful.
I see, that's interesting. So there is a lot of community support.
There is a lot of community. I think we owe quite a bit to the overall hype of the technology. So people were willing to give us the benefit of the trust and invest into learning the technology.
I see, that makes sense. Thank you.
Mm-hmm. All right, okay, moving on. So now we have the language. So what should we do? Well, we should see how good it is. And this is absolutely by far the most difficult part of doing research in programming languages. You know, in programming languages, the effects of taking certain decisions, they are not very easy to demonstrate on a short scale. Like, it's not like okay, obviously we are like happy to find like attacks or show like improvement in terms of performance on the state of the art. And those are the papers that are easy to publish and points that are easy to sell. But if you come up with a new programming language, how do you show that it's a good programming language? Because this is something that cannot exist in isolation. You need the ecosystem. You need to have some empirical proof that this programming language indeed solves certain problems, and that might take literally decades of work. So like even things such like as popular as Rust nowadays, it took more than 10 years for it to take off and multiple iterations in the design. So Scilla has been existing for over 3 years. So I cannot like say definitely that we hit all the right spots, but in the short term, like how do you even bootstrap the language? So, okay, first of all, you check the expressivity by hiring a team of talented engineers and asking them to learn the thing or two about the blockchain and write a number of functions. So we implemented the standard library. We implemented a bunch of contracts that like kind of a very obsolete figure from 2 years ago, but that's what we started from. So if the names don't say much to you, I can tell you that ERC 721, that's essentially the standard that everyone is using for NFTs nowadays. So yeah, this was clearly implementable, and also we could implement certain games. So okay, so expressivity, I think we had it checked, and then we rolled it out to the community and tried to collect the feedback about what features they needed, and then we very conservatively introduced those features to the language or explained how they can be expressed in different things. And there is actually a cookbook nowadays that tells how to program in Scilla. So what's kind of more difficult to assess is how good is the language for the original claims. So yeah, so it comes with this model, but there is a significant, like there is still an effort to getting back to Coq. So in the short term, what we try to prove is that having a language that's simple makes it very easy to extract certain properties for it. So we build a small framework for static analysis, and we immediately instantiated with Swiss2. So first, like to see how much gas construct use. I didn't really talk about gas model that much, but let's mention that all programs, they have some intrinsic costs initially associated with their execution. And second, whether people use the integer as a consistent representation of money. So we didn't really want to introduce dedicated data types for money or different flavors thereof or tokens and whatnot, but instead we're confident we can check the consistent usage of integers in particular sense, such as money, using the static analysis. So for gas usage analysis, again, there is quite a significant amount of research in analyzing functional programs for resource consumption and also for do it in a modular way. So in particular, somewhat 7-8 years ago, I co-authored this paper, which implemented a similar analysis for how many times certain parts of the functions are used in Glasgow Haskell compiler. So that's now part of the standard code base. So basically what we did, we took the ideas from that fork and we transferred to derive complexity signatures of the function. So here is a standard function map, which takes a function, takes a list, and applies this function to all elements of the list, returning the new list. From that description that I gave, you kind of probably guess what the complexity of it is in terms of the size of the list. So, and this is exactly, so it's linear, and this is exactly what our analysis derives. So it gives you that the gas consumption, some constant time A, plus constant time a times b plus 11, where b is the cost of calling a function and a is the end of length of the list. So you can see it's actually linear in the size of the function and also has the cost, the worst case cost execution of the function as a factor. So it's the analysis works well for deriving linear and quadratic complexity. We can probably beef it up with using master theorem, but turns out that was already surprisingly efficient in detecting when people write the code that is not optimal. So people actually use this analysis quite a bit. And now it turns out that we can use this analysis for also partial evaluation in the compiler, but that's another story. So cash flow analysis was kind of a single sanity check, and there is an abstract domain, and there is some way to assign what is money and what is not money and track the flows from the money fields to non-money fields. And overall, we applied it initially to the contracts, and we got the asymptotic gas usage, which seemed entirely in line with how the functions were written. And we also checked that all the contracts that we have written, with some domain-specific exceptions, they actually did preserve the cash flow. So the NFT was slightly tricky because NFT didn't deal with cash per se in many of the methods. It was dealing with these non-fungible tokens that were managed between the parties. So that's where the analysis slightly lost the precision. Okay, so overall, there are more points to prove about this, and if you're interested, there is a paper which we published 2 years ago, and that's the paper which meant the overall design document for the language. And that could be the end of the big programming language story, but in fact, this is where it only has started. So since we launched Scilla on Zilliqa in June 2019, there were hundreds of community contributed contracts. So this is responding to what Mark said. So different standards, NFTs, access controls. There was one contract that raised like literally millions of money just by selling domain names. And this was the logic implemented in Scilla. There are plugins written outside of the team. So Emacs plugin, VS Code plugin, LSP, and even the workshop and tutorials. So I unfortunately do not read Japanese, but this is something that warms my heart quite a bit, like to see tweets like this when people are being taught the language. So, and there is an online IDE in which you want, like, which if you Google for Scilla ID, you can find it easily and you can try it yourself. All right, and there is a block explorer which you can find all the contracts deployed today and like see what exactly are the patterns that people exercise. Okay, so that was the safety net part of the talk, and I think I want about 10 more minutes to talk about the jump part, but this would be as good time as any to see if there are any questions. All right, let me move on. So the second part of the talk is a piece of research that has been done in collaboration with George Perle, one of my PhD students, and also people from Zilliqa. So, and this is where, like, I want to show how principles and the programming language design start paying off in the areas where you could only hope that you can get something. Okay, so here's the problem. So Zilliqa's main contribution was the fact that it produces sharding. So what's the sharding? So sharding is a solution to scalability problem in distributed systems. Here's the main punchline. Blockchains, as we know them from the simple definition in Bitcoin and Ethereum, they scale really, really poorly. So the idea is that the blockchain, we have these nodes and we have the replicated state, and then we might have a bunch of contracts in it. And then when a certain transactions come, well, the whole network needs to agree on which transactions go where and on the order. So this is the setup that I've explained. So now if we have more transactions, guess what? They will still go through the same network, and pretty much every single participant, okay, at least in the majority will have to agree on that. And this is how we progress from one block to another. But if we have more transactions, clearly we have problems. So nodes have limited bandwidth, and so does the network. They also have limited processing power. So the simple solution is to split the whole network into the mutually disjoint components, and then allocate, let's say, contracts to these components. So whenever we have contracts dedicated to particular contracts, they are not processed, transactions for particular contracts, they are not processed by entire network, they are just processed by part of it, which is called shard. And this idea, obviously, as anything cool in the system, has been invented in the database community in 70s or 80s. So yeah, so we are just taking it from there. So, but if we adopt it like this, sharding has its limitation. So, and the problem comes that like not all the contracts are used the same way. Sometimes we have a very, very popular contract, such as this fungible token, which is the essentially crowdfunding campaign that everyone wants to donate to. And then the whole pressure goes onto one shard. Okay, so in principle, what we want to do is somehow replicate this token between the shards. But then if we start updating that in disarray, the state of the contract might get inconsistent. And this is something that has been recognized, so we can engineer another consensus protocol on top of the one that is taken within a chart, so something that two-phase commit, and that comes with a whole bunch of bugs. So the problem is, can we phrase it differently? Can we just look at the contracts and state, well, is this contract something we can possibly execute in parallel without really needing to reconcile the things and then just do something simple as three-way merge? In other words, does the contract define a shardable state machine? Can we parallelize it? And turns out that this is a question that programming language designers and compiler engineers answer all the time. Does the code have a certain property? Yes. So we can actually mine this property from the contract code using the techniques from programming language research, such as static analysis, and uncover opportunity for sharding the contracts or replicating them consistently across multiple shards. And the idea is actually super simple. So there are essentially two mechanisms that make it possible to run parallel computations without the fear to step on each other's toes. Either we try to identify certain opportunities for disjointness, and whenever we deal with disjoint state, obviously like, there can be no conflict. So for example, if you look at this fungible token, which is the crowdfunding, you can notice that in fact, most of what it does, it just updates the map of the backers. So if we consider this map of the backers to be something that can be split virtually into multiple disjoint maps, well, there we go. We got our disjoint. So in fact, now we can replicate the multiple copies of the crowdfunding such that each shard will be responsible for updating a disjoint portion of the backers. And this is how we leverage the disjointness or state ownership. There is another mechanism that everyone knows about, which is commutativity. So here, if we have a contract that just increments the counter, obviously we can do that in parallel and then just take the deltas and do the three-way merge. So commutativity of the addition is something that enables that. So, and if we increment the counter in parallel, the cumulative result can be obtained by joining the contributions or the deltas from each shard, and again, we don't need the consensus. This is actually something what is already done in Zilliqa for plain accounts. So for example, if we have 4 accounts, A, B, C, D, you can see that A transfers money to B and C, 10 one way and 20 another way. And if it does it in parallel, then in fact, it might double spend. So imagine it only has like 25. So then it can send 10 according to one shard and can send 20 according to the other shard. And now we have a problem. But if we also look, but this is why, and this is because subtraction is something that needs to, like, cannot be really parallelized. It really needs to be handled sequentially in order to avoid these things. However, addition, which is commutative, is what happens towards the contract, the account C, which gets plus 20 and plus 15 from both A and D. So in fact, these contributions is something that can come in arbitrary order because that still commutes. And if we take these deltas, we will still know that C will get 35. So in fact, these sort of transactions can be processed in 2 different shards. And there is no need to kind of assign C to a particular shard. So its copy might be in any shards, assuming that they exchange deltas at the end, for which no extra consensus is required. So here we actually need to be very careful when we talk about commutativity, because even if we have commutative operations, they don't mean that they commute with each other. For example, here we have incrementation and multiplication by 2, and obviously, depending on the order we compose these 2 transactions, the result will be different. So like composing double and double will work, composing incrementation will work, but yeah, not another way around. Okay, so roughly what the static analysis does. So static analysis looks at the code of the contract in the very same compilers do analyze the code, and it produces what's called the effect summary, telling what it, deriving what it writes, what it reads, and how this information can be used to see what parts of the state certain transition touch and whether it uses certain commutative operations. So, and then we determine which effects contribute commutative changes, using, well, something that we call linearity tracking flows to analysis, but in fact, it's also something that they use in compilers that do automated parallelization. So we actually invent very little here. So, for example, here in this transaction, we know that in order to make a transfer, the shard should own the portion of the map that is defined by sender. But it doesn't need to own the portion of the map balances that is ascribed to the receiver, the to field. So because there, the changes are going to commit. Okay, so how does it work? This actually works pretty simple. So the contract writer gives this contract to the analyzer and tells which transitions she wants to try to run with the maximum degree of parallelism. So the analyzer produces these summaries and passes them along with the client's request to the solver, and it introduces what's called the sharding signature. So the sharding signature is now kind of an additional passport that is assigned to the contract. So this signature, this constraints, is something that is going to be taken into the account when the transactions are routed into one shard or another. And they are very easy to check. And there are also some, and so basically this is us producing the parallelization strategy for the transactions in the blockchain. So the way it's integrated, so this is a very high level picture of Zilliqa. So we have 3 shards and we have incoming, like swarm of incoming transactions at the end that all go through the lookup nodes. So now the lookup nodes, they're aware of this sharding constraints, commutativity and ownership information. And whenever a certain transaction comes, the lookup nodes can check which contracts it's going to interact with and whether the constraints that these contracts impose allow it to be forwarded to the shard, or if it cannot be sharded, it's forwarded to the fully sequential part of the protocol, which is called directory service committee. So this is a shard at the top. So overall, it turns out that most of the transactions to common contracts can be parallelized, and this is something that we explored. So we integrated with a branch of Zilliqa. It's not yet in the production, but this is something that is going to make it very soon. So as I said, the transactions are dispatched based on the constraints that the analysis have inferred for particular contracts that this transaction touch. And then the contributions from the parallel executions are merged using non-conflicting. So this is a pessimistic concurrency. We know that it commutes, like there will be no conflict. They are merged in the three-way, in the three-way merge-like way, right? Okay, so getting to the end. So we evaluated it. So in addition to parsing and type checking contracts, like running basic verification checks, when we deploy them, we also added the sharding analysis, which introduces noticeable but not particularly large overhead. It's certainly not larger than the type checking, so the analysis is very performant. You see it takes microseconds. But it actually enables quite a lot of parallelism. So we take common contracts and we take common transactions that run their transitions, and we run multiple of those transactions, and you can see that for something like fungible token or non-fungible minting and transferring, we get a linear scale up in transactions per second. So the vertical axis is transactions per second. It's not a very, it's not a very performant network. I think we can do better. So, but we have a linear scale up of transaction per second throughput, dependent on the number of shards for most of the transitions. So not for all of them. I can tell you more if you're interested, like why we didn't get the speed up everywhere. Okay, so there was a paper that came out of it. It was on PLDI last year called Particle Smart Contract Sharding with Ownership and Commutativity Analysis. To summarize what we have done, we took the solution which was already existing, but didn't allow to integrate smart contracts very easily. We used the programming language techniques to some determine conditions under which parts of contracts might be executed parallel, and we built essentially what's the parallelizing compiler for the blockchain, which was very easy to do for Scilla. And as far as I know, something like this is now, like people from Ethereum community are trying to adopt that, but they are very far from there yet. Okay, to conclude. So I have shown you the journey of designing, adopting, and harnessing the power of programming language design for this exciting area of blockchain programming. So personally, I would like to put some takeaway points, but I'm thinking more interesting is like put my own lessons learned, the lessons I've learned from this. So first of all, it was really thrilling, and still is really thrilling, a journey to grow a programming language, see how it's being used, and experience this excitement when you see people like use it as you intended, and angst when people obviously use it as you not intended. And this is something that you need to embrace and adopt it. So if you want to design your own language, like usually going with functional programming paradigms, higher order functions, polymorphic types, is a good way to keep the language minimalistic yet very expressive. Lots of ideas from programming language research, they are quite paramount, like type semantics analysis can be reused with very low overhead for multiple domains. So this was about blockchains, but you can see multiple success stories in programming language for computer architectures, for GPUs, for ML, and this is just one snapshot of applying the techniques. And finally, the principal design of the language very frequently enables applications beyond just reason about correctness and safety, such as what we have seen parallelizing compilers for consensus protocols. So with that, let me conclude and just mention a bunch of directions that I'm very excited about and we are pursuing. So we are still finalizing the compiler from Scilla to Coq for verifying functional properties. We also embrace the lightweight verification where people don't have to write proofs at all, so they can have the push the button. So we have a compiler from Scilla to the TLA Plus, which is a bounded model check-in. We have a proposal to enhance this with proof carrying code, so submitting proofs along with the contracts, which are even easier to check than the contracts. There is a work on type and gas preserving compilation into LLVM. So gas preserving part is actually very challenging. And well, I'm very excited to explore more opportunities for boosting up throughput, doing transaction sharding and parallelism, and looking at new techniques such as rollups and how the programming languages can help it. So if you're interested, this is an address of our lab, or you can just Google Verse Lab in US. And this is all I have. So thank you. I'll be happy to have questions now.
Thank you. I think we have sufficient time for questions. Maybe I'll get started. So one of the things among the work in progress that you mentioned, so do you envision that every contract that is written, you will have a Coq proof for it to verify the property, or?
Okay, so currently that's obviously not the case. So the question is, do we have a Coq proof for any contract? So the way the language is designed makes it very straightforward to translate it from the language. Oh, thank you, Seth. Okay, so it makes it very easy to translate the program in Scilla into a program with Coq and ascribe it these properties. So and then, well, you have the power of Coq at the palm of your hand. So, but again, obviously, this is not something that comes for free. You need to write the properties and you need to write the proof. The only thing that the programming language design spares you is that, okay, so let's talk about how you verify programs in Coq. So Coq has foundational proof framework. It's not something that is custom tailored for a particular language. You can implement verification framework for any language, but it doesn't come for free. So you need to have the semantics of this language embedded into Coq, and you need to have like proof principles and lemmas embedded to you. So this is something that we already give to you. So you get Scilla, you translate it to Coq, it already comes with hardened semantics. So the only thing you need to do is to write theorems and write proofs of those theorems, which is a big thing, but that's not as much as implementing this whole verification framework from scratch. That said, that's a fair point that writing fully like theorems and higher order logic and proofs of those is not for the faint-hearted. So I have a lab of people trained to do that. So, but I cannot expect that anyone can do it right away. So that's why we invested into a compiler to TLA Plus, which gives you weaker soundness guarantees because it doesn't prove universal properties. It proves them on the bounded space. But this is something that you have like essentially push the button. So we translate the Scilla to TLA Plus. We have some dictionary of specifications someone can choose from, and then push the button, like wait for a few minutes and see if some violation is found or not.
Thanks.
So I have another question, which is sort of related.
Yes.
So yeah, somehow I got a sense that the loops were supposed to be sort of bounded. The bound has to be statically sort of encoded, determined.
That's right. So we don't have while loops. We have only for loops, so to say.
And that is also the case with recursion, like recursion.
Yes, so that's a good point. So we don't have explicit recursion in the language. So the only recursion there is, I mean, actually, the semantics of the language has a recursion operator, but the programmers don't have access to it. So the premise is that if you want to have a recursion, most of the time you really want to have an iteration over a certain recursive data type. And this is how you implement that. So we actually thought about making it slightly more permissive and allowing for structural recursions, like provably terminating thing. But that requires to implement a syntactic termination checker, which is feasible, but well, we didn't really see that much demand for it. So people were like fine just writing iterative computations.
So if that's the case, then why not just have a push button verification? Even if PLA plus, why not just?
Yeah, okay, so push button sound verification is difficult because we have a higher order language. So I don't think you can. Okay, okay, so here I'm not really an automated verification person, so that's more like your area of expertise. But I find it very difficult to coerce the high order properties into something that you can verify fully automatically, unless you're like an EPR or a similar logic where you can express them.
I see. So it's not really the case that the state space of this system, I don't know what is the system, but let me just generically call it a system. That's not like a bounded state space or finite state space.
Well, no, it's not, because you have unbounded space of parameters, of input parameters.
You mean the environment interactions, that thing?
Yes, I mean, okay, so people can send arbitrary integers.
I see. Okay, makes sense.
Yeah.
So actually one more question.
Yeah.
So that the paper, Scilla paper, says automata for something. So
yes.
What does that mean, automata?
Well, okay, so that was an initial proposal, and the stress of automata was that on the automata aspect was, I mean, I was really inspired by the input-output automata, but made it deterministic. And the idea is that the contracts, they are reactive entities that receive the messages and either relay them or just do some changes in their internal state.
I see. So it doesn't necessarily have to do with like a finite state.
No, not that kind of.
Okay. Thank you.
Thank you. There's a question from Mate, and I don't think I can give a satisfactory answer. So Mate is asking, how does this work relate to Ethereum ACT? So Mate, can you maybe educate me on what it is? Because I don't think I can click this link now. No, your mic doesn't work. Okay, so I'll be happy to take this offline, so you know where to find me.
Yeah, we have time for more questions. Maybe I'll ask one last question. How about, are there also other properties that you may be interested in verifying in sense of the hyper properties you seem to be focusing on?
Good question. Hyper properties, what about those? So okay, my knowledge of hyper properties kind of is frozen 5-6 years ago, when people only cared about information flow. Since there is no private data here, I don't know how to phrase information flow properly for smart contracts. But if you can suggest other things, I'm sure we can probably adapt that to something. I mean, okay, in Coq you can state any property. The point is that which of those we can verify in a decidable manner.
Okay. Yeah, I mean, my knowledge about hyper properties mainly have been restricted to information flow or quantifying it. But I guess here it's not clear what you want to protect or so.
Yeah. But this is a really good model for experimentation. So if you have a bunch of properties, so we started. I mean, I'm not an expert here, so because there's only so many hours I have in the day, but we started to look at the DeFi protocols where there are like this distributed decentralized finance protocol, where there are really complex interactions between multiple contracts, and this is where the trace properties start being like very hairy, and I'm not sure you can always get away with safety properties. So sometimes you really need to state the liveness property too.
So if I can ask one last question, something that I didn't follow, is it, are you able to show that certain kind of attacks that are possible on blockchains won't happen in the language that you designed, in sense of like collusion between certain percentage of agents or so on?
Well, depends. Okay, so there are lots of local properties of the contract that you can ensure just by means of type safety. If you want to prove the properties that involve interactions, then you need to write Ethereum and encode the composition of those contracts. So yeah, that's as much as I can say without going into details.
Okay, so Mate.
Can you hear me actually now?
Yes, I can.
Oh, that's perfect. Sorry, Linux is always complicated. Yeah, this ACT is apparently a system that is a language designed to express contracts and then verify them with, for example, COC, and of course, it's transpiled into Solidity. So it's basically a higher level language that you would eventually, translate the language. The contract that you write into a Solidity, and then you do your verification on this ACT system. And of course, ACT is designed in a way that is easier to verify, and so there are plans, at least, to verify it with SMT, COC, and some other systems as well.
Yeah. Okay, I see. Okay, though this is actually one proposal of many I can think of. So there are other languages that also try to compile essentially from COC to either Solidity or directly to EVM. So there is Deep Sea, which comes from Yale and Columbia. So they come later than Scilla. And well, you still have this notion of trust in the sense that you need to know, okay, if you are the designer of the contract, that obviously is a good thing for you to have. So you can have all the properties that you want. If you are the user of the contract, it's something less of a use for you because typically you will still face a contract that is deployed in EVM for which you don't know how it came and what properties were proved about it. So being able to have it in the language which is more amenable to verification right away, and this is something that's deployed. That was one of our goals.
I see. Yeah, I think some systems like Ethereum, you're not going to change the language of Ethereum anytime soon. So I think the best option they have is to use something like ACT or some other higher level language and then transpile. But of course, that that doesn't necessarily apply to a system that you design from scratch.
Thank you.
Okay, so I guess that brings us to the closing of today's colloquium. Thanks again, Ilya, for a very interesting and engaging talk. We are going to close this week's colloquium. We'll be meeting in 2 weeks. So again, instead of Wednesday, we'll be meeting on Thursday. So thank you everyone for joining. See you in 2 weeks. Thank you again, Ilya.
Thanks, Kodeep. Yeah, have a good one.